A-level mechanics, elastic strings, Hookes law. Let's see what we mean by elastic strings and Hookes law. Up until now we've talked about strings that are inextensible. That means they can't be stretched. They maintain a constant length no matter how much tension they're in. However, many strings or springs will extend under tension. We call such a string elastic. Now we're going to assume that elastic strings have the following properties. 1. They have a natural length when they're not under tension. If they are extended under tension, they will return to their natural length once the tension is removed. 2. When they're stretched, the work done in stretching them is stored in the string and can be regained as the tension is removed. In other words, no energy is lost in heat or sound. And thirdly, they obey Hookes' law. We'll go through that in more detail later, but it says the tension in an elastic string is proportional to the extension. Now these are reasonable assumptions up to a point. In real life, they are found generally to be true, but if the stretch becomes too much, an elastic band will break, or the material may be permanently deformed. The point where this occurs is called the elastic limit. Only if the stretch is below the elastic limit do the above assumptions apply. Now let's look at Hookes' law in detail. Hookes' law states that the tension in an elastic string is proportional to the extension. In the diagram we can see a string of length L that is stretched by an amount x under a tension T. So T is proportional to x, which means we can write T is equal to kx, where x is the extension. Here, K is called the stiffness of the string or spring and has units newtons per meter, or Nm to the minus 1. However, the stiffness K only applies to a particular piece of string or a particular spring. If we have a second string of the same type as the first, but twice the length, we would expect twice the extension under the same tension. So we have T is proportional to x over L. In other words, T is equal to a constant lambda times x over L, where x is the extension and L is the natural length. Then lambda is called the modulus of elasticity and is independent of the length of the string or spring. In the case of a spring under compression, x will then be the reduction in length from the natural length. We can see the units of the modulus of elasticity are newtons, the same as for force. Now we can get an idea of what stiffness feels like if we consider the equation T equals kx and let x equal 1, in which case T is equal to k. And so we can see K, the stiffness of the string, is equal to the force needed to extend the string by 1 meter. In a similar way, we can get a feel for the modulus of elasticity if we consider the modulus equation T equals lambda x over L. Now if we let the extension be L, then we get T equals lambda L over L, or T is equal to lambda. And so we see lambda, the modulus of elasticity, is the force needed to double the length of the string. Let's have a look at an example. A light spring of stiffness 60 newtons per meter and length 50 centimeters is placed vertically on the ground, and a block of mass 1.2 kilograms is balanced on its end. Find the height of the block above the ground. Well, to solve this, first, on the diagram, draw in the forces. On the brick there's a weight of 1.2 g acting down and a thrust P from the spring acting up. We can then resolve vertically on the block. We get P is equal to 1.2 g, which is 1.2 times 9.8, or 11.76 newtons. Now if we let x be the compression in the spring, then we have T equals kx. So 11.76 is equal to 60x. Then, dividing both sides by 60, we get x is equal to 0.196 meters. So the compression in the spring is 19.6 centimeters. And the height above the ground is the original length 50 minus 19.6, which is 30.4. And so our answer is the height above the ground is 30.4 centimeters. Let's have a look at another example. Example 2. A string of natural length 2.4 meters and modulus 88.2 newtons is suspended from a fixed point A. A mass of 1.8 kilograms is suspended from the other end at B. Find the total length AB. Well, to solve this, first, on the diagram, mark in the forces. There's the weight 1.8 G and the tension T in the string. We can then resolve vertically, and we have T is equal to 1.8 G, which is equal to 1.8 times 9.8, or 17.64 newtons. Now, if we use Hooke's law, T equals lambda x over L, we have 17.64 is equal to 88.2 times x over 2.4. We can rearrange that to get x is equal to 0.48. We now have the total length is 2.4 plus 0.48, which is equal to 2.88 meters. And so our total length AB is equal to 2.88 meters. In example 3, we're told that when an elastic string is under a tension of 6 newtons, it's 2 meters long. When it's under a tension of 21 newtons, it's 3 meters long. We're asked to find what is its natural length and the modulus of elasticity. Well, to solve this, let the natural length be A. Then, suppose it has an extension of x under a tension of 6 newtons and an extension y under a tension of 21 newtons. In the first case, we have the total length is 2, which means x is equal to 2 minus a. In the second case, we have a total length of 3, and so y is equal to 3 minus a. Now, using Hooke's law, which is T equals lambda x over L, we have the tension 6 is equal to lambda x over a, which we can write as 6 equals lambda into 2 minus a over a. Now, when the tension is 21, we have 21 is equal to lambda y over a, or 21 equals lambda into 3 minus a all over a. Now, if we divide equation 2 by equation 1, we get quite a complicated fraction, but it cancels down. 21 over 6 cancels to 7 over 2, and on the right-hand side, the lambdas at the front cancel, and the a's under each fraction cancel. And so we have 7 over 2 equals 3 minus a over 2 minus a. Now, if we multiply both sides by 2 and 2 minus a, we get 7 into 2 minus a equals 2 into 3 minus a. Expanding the brackets, 14 minus 7a equals 6 minus 2a, which we can simplify to 8 equals 5a. So if we divide both sides by 5, we get a is equal to 1.6 meters. Now, if we substitute that back into equation 1, we get 6 equals lambda into 2 minus 1.6 all over 1.6, which simplifies to 6 times 1.6 equals lambda times 0.4, and if we divide both sides by 0.4, it works out lambda is 24 newtons. So our answer is the natural length A is 1.6 meters, and the modulus of elasticity lambda is equal to 24 newtons. In example 4, an elastic string of length 1.6 meters and modulus of elasticity lambda is attached to 2 pegs A and B 2 meters horizontally apart. A mass of 0.8 kilograms is attached to the midpoint C of the string. In equilibrium, AC makes an angle of 25 degrees with the horizontal. find lambda. Well, to solve this, the first thing to do is draw a diagram and mark in the forces. We can see the diagram will have vertical symmetry. There are three forces on C. There's the weight, which is 0.8 g, and there's the tension in each of the two parts of the string. They'll be equal, so we'll call that tension T. Now it's worth marking in the angles between the string and the vertical, and they'll both be 90 minus 25 or 65 degrees. Now to resolve vertically, we want the force times the cosine of the angle between the force and the direction. So we've got two forces of T at angle 65 degrees, and so we have 2t cos 65 is equal to 0.8 g. Dividing both sides by 2 cos 65 degrees, we get t is equal to 0.4 times 9.8 over cos 65, or 3.92 over cos 65. And that works out t is 9.27551. Now if we look at the triangle ACD, we see that the side AD is 1 metre. So the sine of 65 is AD over AC. AD is 1, and AC is the extended length of the string. Now, the mass is at the midpoint of the string, and so on either side there's an unextended length of 0.8 metres. So the full length AC is 0.8 plus the extension of that part of the string x. So we have sine of 65 is 1 over 0.8 plus x, or 0.8 plus x is equal to 1 over sine of 65 degrees. So x is 1 over sine of 65 minus 0.8, which works out to be 0.3033779. Now we've got from Hooke's law, T is equal to lambda x over L, which can be rearranged as lambda equals T times L over x, and we know T, L and x. X in this case is 0.8. So that gives us lambda is equal to 9.27551 times 0.8 over 0.3033779. And that works out to be 24.459. And rounding that off to one decimal place, we've got the modulus of elasticity lambda is equal to 24.5 newtons. Example 5. An elastic string with modulus of elasticity 19.6 newtons has a mass of 2.25 kilograms attached 1/3 of the way down it. It is stretched with one end attached to the ceiling and the other end attached vertically below to the floor, a distance of 3.6 meters. In equilibrium, the mass rests exactly halfway between the ceiling and the floor. Find the length of the string. Well, to solve this, we need to draw a diagram, and then let the length of the string be 3a. So AB is A and BC is 2a. And then draw a diagram of the string stretched between the ceiling and the floor. Now the mass hangs 1.8 meters from the ceiling and 1.8 meters from the floor. So the top part of the string is stretched by an amount 1.8 minus a, and the lower part of the string is stretched by an amount 1.8 minus 2a. Then we can draw in the forces on the diagram. First we've got the weight, which is 2.25 g. There's a tension in the top part of the string that we can call T, and there's a tension in the lower part of the string which we can call P. Now using Hooke's law, T equals lambda x over L, we've got T is equal to 19.6 times 1.8 minus a over a, and P is 19.6 times 1.8 minus 2a over 2a. Resolving vertically on the mass, we've got 2.25 g plus P is equal to T. So substituting those in, we've got 2.25 times 9.8 plus 19.6 times 1.8 minus 2a over 2a equals 19.6 times 1.8 minus a all over a. If we divide both sides by 19.6, that gives us 1.125 plus 1.8 minus 2a all over 2a equals 1.8 minus a all over a. And if we multiply both sides by 2a, we can cancel down, and that gives us 2.25a plus 1.8 minus 2a equals 3.6 minus 2a. Well, the minus 2a cancels on both sides, so that simplifies to 2.25a is 1.8, and if we divide by 2.25, we get a is 0.8, and so 3a is 2.4. Now the length of the string is 3a, and so the length of the string is 2.4 meters. Now, although it comes up very rarely in mathematics, it is probably worth mentioning Young's modulus. If we've got two lengths of elastic string made from the same material, but one has twice the cross-sectional area of the other, we would expect it to be twice as difficult to stretch. So the tension in the string would also be proportional to the cross-sectional area of the string. We can call that A. And so we have T is proportional to A over L times X, or we can write T is equal to EA over L times X, where E is the constant of proportionality and is known as Young's modulus. Now, Young's modulus does not depend on the dimensions of the string at all. It only depends on the material from which it's made. So Young's modulus is used far more when discussing materials rather than actual strings. This means Young's modulus is commonly used in engineering or physics, but not so much in mathematics. It's more to do with the properties of materials. Young's modulus could not be used for springs because springs are not solid materials.